Welcome back to Pre-Calculus Unit 8. We are here in Lesson 2, and our learning target is to continue plotting points using polar coordinates. So this is the second part of Learning Target 8A. In our last lesson, we focused on how to plot individual points. So given a radius and an angle, how would you plot that on the polar coordinate graph? Today we are going to extend that to plotting functions by creating a table of values and then making a series of points. So two things to be aware of before we get started here. First thing is that most of the angles given in today's lesson are going to be in radians. So you're going to want to hit the mode button on your calculator and then make sure that you are in radian mode. So make sure that radians here is highlighted and hit enter. The other thing that you're going to want to remember is how to get the pi symbol, and that is the second function on the caret key. So right there, if you hit second and then caret, you will get the pi symbol. We'll be using that a lot in the calculator today. So make sure that you're in radian mode, make sure that you know how to get the pi symbol. And then let's get started with some examples here. First one, we have r written as a function of theta. So r of theta is equal to theta plus 2. So you might be familiar with an equation that looks something like f of x is equal to x plus 2, or y equals x plus 2. That would be a linear equation. But in polar coordinates, let's see what happens when the radius varies with the angle that we are graphing. So the first part is just plugging a bunch of numbers into the calculator and seeing what we get out. We are not going to be able to graph these with a lot of super precise decimals, so I'm just going to round my answers to 1 decimal place. The first angle that I'm given is easy. It's 0. So r equals theta plus 2 is going to be 0 plus 2, which is just the number 2. From there, we've got r equals theta plus 2 with an angle of pi over 6. So pi divided by 6 plus 2 is about 2.5. So we see that my radius has increased a little bit. Next angle is pi over 3. So the radius at that angle measure would be pi over 3 plus 2, which is about 3.0. Then I've got pi over 2 as an angle, so pi over 2 plus 2 is about 3.6. And continuing on, 2 pi over 3 plus 2 is about 4.1. 5 pi over 6 is the angle. Angle plus 2 gives us a radius of 4.6. And I'm just going to pause here and fill out the rest of the chart. I'm sure you guys could do it on your own. And here we go with the rest of the chart filled in. I get values of 5.1, 5.7, 6.2, 6.7, 7.2, and 7.8. Now we want to plot each of these points in order to create a polar function graph. So having just one point is interesting enough, but graphs are far more useful. So let's see what this ends up looking like. So my first point, I have an angle of 0 and a radius of 2. So I am going to go 2 units towards this angle of 0. That first point lands right there. Second point, I have an angle of pi over 6. And the radius I calculated was about 2.5. So I'm going to go 1, 2, and about a 0.5 towards that angle. And then I'm going to keep going. My next point, I have an angle of pi over 3. So I am now up here and a radius of 3.0. So I'm going 1, 2, 3 units towards that point. And then continuing on around at pi over 2, the radius is 3.6. So 1, 2, 3, and just over a half. At 2 pi over 3, I am now over here, and my radius is 4.1. So starting at the center, going towards the angle measure, 1, 2, 3, 4, and just a little hair beyond that, about there. And then continuing on, at 5 pi over 6 as my angle, the radius is 4.6, so 1, 2, 3, 4, and 0.6, so just over a half. And then 5 pi over 6, we already did, so I'm jumping down here now to pi, and the radius is 5.1. So at an angle of pi, radius 1, 2, 3, 4, 5, and a 0.1. And then continuing on, I've got 7 pi over 6, radius 5.7, 4 pi over 3, radius 6.2. And then I'm going to run out of space on the graph here pretty soon, but at 3 pi over 2, my radius is 6.7. And then at 5 pi over 3, we're officially off the graph just by a little bit, 7.2. And I can probably make an estimate here, 11 pi over 6, 7.8, probably about there. So we've got a bunch of different points, and now we want to connect the dots. Connect these as smoothly as possible and see what kind of shape does this make. So I started here at 0 and 2, and then I drew all of these other points in. Now I'm going to connect them. Straight and smooth as I can. And the shape looks something like that. So it's a nice little curve here. It's a spiral shaped curve, where as the angle gets bigger and bigger and bigger, the radius, or the distance from the origin, also gets bigger and bigger and bigger. And if I were to keep going, this spiral would keep on curving outward and outward and outward. So that's an example of a polar graph that is a nice shape to be able to model. There's no way that you could draw that easily using x and y, but it's a very simple equation, just theta plus 2, when we graph it using polar coordinates. Let's look at another example. Here we have the function r of theta is equal to the square root of 9 times the sine of 2 theta. And again, I'm given a table of values that I want to plug in for theta and see what radius we end up with for each one. So I'm just going to plug these into the calculator all in one big step and let it do the heavy lifting for me. So my first angle to plug in is 0. So I'm going to do the square root of 9 times the sine of 2 theta becomes the sine of 2 times 0. And you'll need probably 2 sets of closed parentheses there. So if I do the square root of 9 times the sine of 2 times 0 and close parentheses, I get a value of 0. So when the angle is 0, the radius is also 0. The next angle that I'm up for here is pi over 6. So I'm going to evaluate the radius by plugging in pi over 6. It'll be 9 times the sine of 2 theta becomes 2 times pi over 6, all under the square root sign. So typing that into the calculator, 9 times the sine of 2 times pi divided by 6. And I end up with about 2.79. We'll round that up to 2.8 because it's difficult to graph more than one decimal accurately. The next angle is pi over 4, so I would do the square root of 9 times the sine of 2 theta becomes 2 times pi over 4. When I plug that into the calculator, I get 3 even. So at an angle of pi over 4, my radius is going to be exactly 3. When I plug in pi over 3, Square root of 9 times the sine of 2 times pi over 3. I got another 2.8. And when I plug in pi over 2, I get 0. And this is where things get a little bit interesting. Because what happens when I try to plug 2 pi over 3 into this on the calculator? So I'm going along 9 times the sine of 2 times 2 pi over 3, all under the square root sign. Calculator gives me an error. I see error, non-real answer. And I can either quit or go to the source of the error. I'm just going to say quit. That is an error. That means this is an undefined location. Why is it undefined? Well, let's ignore the square root for a second and just do 9 times the sine of 2 times 2 pi over 3. And if I just plug in that part, I get negative 7.79. So when I try to evaluate the square root of 9 times the sine of 2 times 2 pi over 3, I end up taking the square root of negative 7.79. And the square roots of negative numbers are undefined, so that was going to be something imaginary. So it is possible here to have values of theta, or angles for which this function doesn't work at all. Let's see if there are any others here. If I try to do the square root of 9 times the sine of 2 times 5 pi over 6, that also gives me an error. So this is another angle for which the radius is undefined. The sine was probably something negative, so I ended up trying to take the square root of a negative number. But let's continue on. What happens if I plug in an angle of just 1 pi? I get 0. And again, I could keep talking through these, but I'm going to pause the video here, let you practice using the calculator to fill out the chart on your own while I fill out my chart here. So here I've gone ahead and filled in the rest of the chart. I have defined radii for 7 pi over 6, 5 pi over 4, 4 pi over 3, and 3 pi over 2. But then I got an error message again for 5 pi over 3 and 11 pi over 6. Those are both square roots of negative numbers, so it would end up being something imaginary. But now that we've got all of these angles plugged into the table, let's plot the points and see what this actually looks like. So my first point here, I've got an angle of 0 and a radius of 0. So that is 0, 0. It's right at the origin. The next point that I have is an angle of pi over 6, and the radius is 2.8. So 1, 2, almost to 3. Looks like right about there. After that, I have pi over 4. And there my radius is exactly 3 units. So I'm going to go 1, 2, 3, stop right on the tick mark. And then pi over 3, radius 2.8. So pi over 3 is here, radius 2.8. So I've got 3 points kind of clustered together there. And then at pi over 2, my angle is pi over 2, and my radius is 0. So I don't go towards it at all. I am back right at the origin. So when you are connecting the dots, it is very helpful to go in the order that you plot the points. Because as we get more and more complicated shapes, sometimes the connections won't always be the points that are closest to each other. But here I plotted these in order starting at the origin, going to dark red, then to light red, then to yellow, and then back into the origin at green. So we've got kind of a little teardrop or flower petal shape there. Now, we've got some points that are undefined. So at an angle of 2 pi over 3, the point is undefined. There is no graph there. And at 5 pi over 6, same thing. Undefined, no graph. But if I pick back up at an angle of pi, at that angle my radius is 0. So the angle is pi, but I go towards that not at all. That's another point that's on top of the origin there. But now I have some real points that I can plot. At 7 pi over 6, my radius is 2.8. So 7 pi over 6, 1, 2, and a 0.8, about there. At 5 pi over 4, my radius is 3. So going towards this angle by 1, 2, exactly 3 units. Then 4 pi over 3, 2.8 again. So about there. And then 3 pi over 2, this angle here, I have a radius of 0, so that's another point on the origin. So if I connect these dots in order, I started at the origin, then plotted the light blue and the dark blue and the purple, and then went back into the origin at red. And then my last 2 points, again, don't really exist. We had undefined function values at 5 pi over 3 and 11 pi over 6. So that is the entirety of my graph, and it makes a nice little whirligig or propeller type shape. Again, this is clearly a mathematical pattern, but it's one that would have been very difficult to graph if you were constrained to square x and y axes. So we have 2 more functions here. This one is 4 times the cosine of theta minus 2. I'm going to let you fill in this chart on your own, just plugging in all of those different angle measures and seeing what radii or what function values you get out, and then we'll go through plotting the graph together. So I've gone ahead and filled in this chart of values here, just doing 4 times the cosine of each of these different angles minus 2. Now when we plot this graph, we're going to have to be very careful because some of the radii are negative. And so you'll have to remember that when a radius is negative, that means you're going to go in the opposite direction, away from your given angle instead of towards it. So let's just start plotting these out, and we'll kind of connect the dots as we go. So at an angle of 0, my radius is 2. So at an angle of 0, radius 1, 2. There's my first point. Next angle on the chart is pi over 12, and that is a radius of 1.9. So not quite to the 2, but very close there. Next I have pi over 6 and a radius of 1.5. So 1.5. These points are getting pretty close together here, so I'm just connecting the dots as I go. Then at pi over 3, I've got a radius of 0. So at pi over 3, my radius is 0. That is a point right on the origin. So I can kind of connect this back in here. Now, here's where things get negative. So at an angle of pi over 2, my radius is negative 2. So I'm going to go 2 units down away from that angle direction instead of towards it. So my next point connects in down there. Next angle is 2 pi over 3, and there my radius is negative 4. So again, I'm going to be going 4 units away from 2 pi over 3. So 1, 2, 3, 4, and connecting that point in. Next up is an angle of 5 pi over 6 and a radius of negative 5.5. So going away from 5 pi over 6 or towards 11 pi over 6, that's my opposite angle. 1, 2, 3, 4, 5, and a 0.5. I am all the way over here, connecting that up as best I can. Then at pi, my radius caps out at negative 6. So instead of going 6 units towards pi, I'm going to go 1, 2, 3, 4, 5, 6 along the x-axis away from pi. From there, my radius starts to shrink again. So at an angle of 7 pi over 6, my radius is negative 5.5. So 7 pi over 6, radius going negative, so in the opposite direction, 1, 2, 3, 4, 5.5. I am up here. And then continuing on, I've got 4 pi over 3 and negative 4. So going away, 1, 2, 3, 4 units. That is right there. Then we are back around to 3 pi over 2 with the radius of negative 2. So 2 units away from 3 pi over 2, or 2 units straight up. Connecting those dots. And at my next angle, 5 pi over 3, my radius is 0, so that is a point that is right on the origin, not away from it at all. And then I have 2 more points to plot here. At 11 pi over 6, so that is right here. My angle is positive again, finally, positive 1.5. So I'm going to go 1.5 units towards 11 pi over 6, connect that to my previous dot, and then my final point here to graph is 23 pi over 12, this last ray here before we get back to 0, and that has a radius of 1.9. So I'm going to go not quite to the 2, but 1.9 units towards that angle. And you can see the shape that this graph makes. I've drawn it kind of colorfully here. But this is kind of like a heart shape, or maybe a big sort of tropical leaf, where we've got this little loop in the middle, and then a big loop around the outside that comes back in and finishes off the little loop in the middle. So you could think of that as being a sand dollar or a leaf, or whatever kind of shape you think that looks like in your imagination. But the one thing that I would say to be really careful of on graphs like this is to make sure that you connect the dots as you go. It's a little bit like a dot-to-dot puzzle, if you remember those from when you were a kid. Because otherwise you'll end up with a bunch of dots that look something like this. And it's kind of hard to tell how to connect those. Do we connect these ones out here and then come back in? Like, there's lots of different ways that you could connect the dots. So make sure that you don't just plot all the points at once, but that you are drawing in the little line segments as you go. And then you can go back and curve them out and make them pretty if you need to. But connect the dots as you go so you have some idea of the order in which the shape is connected. And we have one final example here. This is 3 times the cosine of 2 theta. So again, you can kind of try this one on your own. Go ahead and pause the graph, fill out the chart, and then we can plot the points here together. So here we go with the chart filled in. I've got lots of 3's and lots of 1.5's. So as we're graphing this, we're really going to have to be careful with when the radius is positive and is going towards the given angle versus when it's negative and is going away from the given angle. So starting off at an angle of 0 and a radius of 1, 2, 3, my first point is right there. My second point is at an angle of pi over 6, and the radius is 1.5. So I'm going to go 1.5 steps towards the pi over 6 angle direction and connect those up right away. My next angle is pi over 3, and here my radius is negative 1.5. So instead of going 1.5 units towards pi over 3, I'm going to be going 1.5 units in the opposite direction, so away from the origin and ending up down here. So if I connect these points, it'll be something like that. Next up, I have an angle of pi over 2, and the radius is -3. So starting at the origin, going 1, 2, 3 units away from pi over 2, connecting it in as I go. Then I've got 2 pi over 3, and again, my radius is negative. So I'm going to be going 1.5 units away, 1.5 units away from 2 pi over 3. Looks like it's right about there. So connecting those points together. Then we've got 5 pi over 6, and my radius is positive again. So radius of positive 1.5. I'm going to be going 1.5 units towards that angle. I'm connecting this point back in with my previous one. Then I've got pi comma 3. Oh joy, so simple. Angle of pi, 1, 2, 3 units straight towards it, connect it up. Next we have 7 pi over 6 and a positive 1.5. So 1 and a 0.5 units right towards it, connect that back. And now I've got more negative angles. So 4 pi over 3, my radius is negative 1.5. So starting at the origin, going 1.5 units away from the 4.3, or 4 pi over 3. Connecting that back to my previous point, something like that. And then just a couple more here, 3 pi over 2, radius -3. So from the origin, 1 and a 2 and a 3 units away from the angle. Connect that up. And then 5 pi over 3, radius -1.5. So -1 and a 0.5 goes there. And to finish it off, I've got one more point at 11 pi over 6, radius 1.5. So I'm going to go 1.5 spaces directly towards the 11 pi over 6 and connect this back to my previous point in purple. And now you can see the shape or the pattern of this graph. It's like a little 4-leaf clover or 4-pronged star kind of shape. We started here and went around and down and around and back up and down, and we came out here, but I bet you can fill in the rest of the pattern in your mind. It's going to come back around to connect where we started to make that little kind of a flower shape. So those are just a few different examples of the kinds of shapes that you can get by graphing different polar functions. We had a spiral, we had sort of a sand dollar, we had a little propeller or pinwheel shape, and now we've got this 4-sided flower or star. So there are lots of different fun shapes that you can come up with if you just play around with graphing different polar functions. Later on in this unit, we're going to be categorizing them and looking at how to predict what the shapes are going to be like. But for now, you just need to be able to fill in a table of values and then plot those points and connect the dots to get some kind of a nice little shape.